Hello everybody, welcome back to another video here at Rule 1 Model Railways. Today we are going to tackle block detection and the use of that in automation. Stay tuned for more. Hello everybody, welcome back to Rule 1 Model Railways. Today we'll be talking about block detection and how does it work with automated control. If you like the content today, don't forget to hit the like button and subscribe. Now moving on, how does it all work? So ultimately, there are three components to computer automation. The first one is the software and computer attached to a command station. The second is the D6C accessory decoders which control the points and other accessories of the like. And the third component is the block detection itself. So of the first component there, we are using the computer to send commands through the command station to all of the different parts of the layout. First of all, we'll talk about the locos. So the computer will be sending speed commands to the loco through the command station and through the track. Obviously the loco receives those and reacts accordingly. The computer software also sends point instructions to the D6C accessory decoders, which set the points to create routes for trains to run. And finally, the block detection units, such as this one here, relay the positions of each train back to the command station, which tells the software where each train is via the loconet. And the loconet is these little cable slots here. They send the information back to the command station, and the command station relays it back to the computer. And that really is the basics of it. Now there is more in depth to that. The software uses speed equals distance divided by time calculations to stop trains and run trains at the correct speed and to stop at the correct point in each block. There are some mechanical variances in each loco, i.e. a cold versus a warm mechanism in a loco causing faster running when warm. So as you know, if you just started a loco off, sometimes it can be a bit slow to get moving, but as you got it running later on in the day, it actually runs a bit faster, a bit better, a bit freer. This can have consequences to the way the software handles the blocks and the trains and the way they run. So to reduce that issue and reduce the margin of error, each block should contain multiple feedbacks. These are basically smaller blocks inside a bigger block. They're wired up no differently from each other. In fact, the software determines which feedbacks are grouped within which block. You can set that up yourself, and I'll show you a bit more on that later. But this does help that error to be factored out somewhat. For example, if you have a feedback with just one, if you have a block with just one feedback, then the margin of error, let's just say it's 10 centimeters. And if you had a block with two feedbacks in it, that halves your margin of error down to 5 centimeters. It allows the speed calculation, speed equals distance divided by time, to be ran twice within the same block, which means you've halved the margin of error. So your margin of error is now down to 5 centimeters. Some of my blocks have 3 feedbacks, and that reduces your margin of error 66%. So it brings it down to around 3.3 centimeters of error. These margins of error that I'm giving you are quite exaggerated, but it gives you an idea of what I mean. If you look in a few of my past videos, a couple of time lapses I'd done, one of the fiddle yard and one of the platforms, you'll see in the fiddle yard, where I only have 1 feedback per block, there's quite a margin of error on some of the trains where the mechanical difference each time it runs around is slightly different. My train with one loop might stop here, and then the next loop it comes around, it stops a little bit further forwards. That's because my train is not 100% accurate, and it needs to be factored out by having multiple feedbacks. Now, it's not that important. It stops in exactly the same place in my fiddle yard every time, so I don't mind that, because I have enough of a run in the fiddle yard that it just doesn't matter. But on my platform side and the scenic side of the layout, it does. The trains have to stop in the same place every time to stop in the platform accurately and not to derail over the points. So, on the front of my layout, I have included multiple feedbacks per block, and that was the reason for doing so. Now, as I was saying there, blocks and feedbacks are differentiated in the software. They're not wired differently on the model railway. The software just allows you to group whichever consecutive feedbacks you want into a singular block. Now, there are cheaper systems out there which work on just using time to determine where the trains are. And the problem with those is that with those mechanical variations with your locos, eventually you'll end up with a train over multiple runs of that same journey that it's been running. Eventually either runs off the edge, over the buffers, or it fails the points going in a particular direction. The reason for this, I would say, is because I have found when speed profiling all of my locos, none of them run the same speed in both directions. They always run slightly faster one way than they do the other. So having iTrain work that out for you, it can actually factor that into its speed equals distance divided by time calculation using the speed profiles you set up for the locos, which is where having feedbacks really plays its part. Really does help. Now I'm going to show you a couple of examples of this, of how my software works. Right here you can see First Great Western 150 02. So that's the second 150 I have. I'm actually going to set the points against it, as you can see here. You can hear it in the background. And then I'm going to route this into my bay platform here, platform 6. And you'll watch iTrain, the software part of that bit that I just spoke about earlier, route the train. It will control the point accessory decoders to set up the route. And when the train moves off, you'll see the feedbacks reporting back where the train is. So here we go. I route it down there. You see it sets up the route. The points are now in the correct direction. The throttle on the train is powering up. And you'll see the next red one light up when it reaches that feedback. This one will go off when it exits that feedback. And that one's gone on when it got into that one. And then it reaches the next block. So the computer's now being reported to that that block is now occupied. The yellow says that this one is reserved. So nothing else can run into that one until this one does. And there you go, it's transitioned into the final block. And iTrain works out how all that works from the calculations, which are run multiple times over the course of the route to stop it in the ideal location at the end. And I am going to get you a video on my handheld system here of the train coming back. So we're going to route it coming back into the fiddle yard, and I'll show you as it comes over into that fiddle yard. So here's a running commentary of how it's working. So it's on the branch line block at the moment, currently running down the branch line block, traversing the junction of points. It's now entering the first feedback of the fiddle yard block. One calculation was run. It's now running another calculation, speed calculation. It's now entering the third block, feedback, sorry, and it's now calculating where to slow down to stop. And as you can see there, it stops fairly accurately, right down to the centimetre. That's how accurate you can have it with multiple feedbacks. But that was just a basic example of how it works. You can multiply this to a whole layout and have a whole layout doing it, or you can just have have your circuits wired up for that and then have your branch lines or sidings or whatever uncomputer controlled. That's not a problem with this sort of software. Now, moving on to looking at how it's all wired up. Here's the diagram that I've used with the hardware I've used. So let's say the computer was down here, where the cursor's circling. It's connected to the USB port. So the software is sending commands to the command station, the DR5000, which is then sending commands down the track bus there, through these, onto the red, and sending information to the locos of what to do. Coming back the other way, on the yellow wires coming back, you can see these blue triangles. They denote a break in the track, which is isolated. And every time a loco is in that block taking the current, it's reporting back to the unit here, the block detection unit, which is then sending information back down the LocoNet cables, back to the command station, and then to the computer, that block, say in here, these little red dots are occupied. That's what that's doing, and that's allowing iTrain to then calculate every single time it goes into a new feedback section there, a new calculation to stop it in the correct place or run it at the correct speed, and gives you that ultimate accuracy in running your trains. And that's really all there is to it. It's that basic. It's not difficult once you get your head around it, but just give it a go. Buy a command station, a feedback unit, and wire it all up and see how you get on with it. It's not difficult at all. It is slightly time consuming sometimes, but the end result's worth it in the end. But that's how feedback works with the software automation. If you've enjoyed the video, do hit the like button, consider subscribing, and I'll see you in the next one. Take care, and goodbye for now.